we're going to turn our attention to vectors. So we've been talking about vectors in this so far. Remember that vector has magnitudes and direction. And the vectors that we have talked about are displacement, velocity, acceleration, and we have mentioned force. So these are all vectors, and we denote that they're vectors with this little half arrow just to distinguish them from other things like speed, which would just be v, and distance, which would just be x. So by definition, a vector has a magnitude and a direction. So we illustrate that visually by drawing vectors as arrows that are drawn to some kind of scale. So if this is 1, 2, 3, 4 inches, we might say that 1 inch equals 5 meters, and this would be 1, 2, 3, 4, 5, or it would represent 1, 2, 3, 4, 20 meters. Okay, and the direction is pointing in the direction. And we're going to talk a little more about how we describe the direction of vectors. We have a couple of options. So let's talk a little more about vectors and how we describe them. So let's just take an example. So far we've talked about distance and displacement, and we said, well, distance is just a sum of the meters or the miles that we've walked, but displacement is the addition of those taking into account the directions. But we only talked about things going east, west, or north, south. They were along the same plane. What's not normal is for us to walk like that, right? We walk all over the place. So let's take an example that's a little more realistic. You're going to walk 2 meters north. So I'm going to draw this to be about 2 meters. So 1, 2, 2 meters north. And then we're going to turn and we're going to walk 3 meters west. So this side is 2 meters and this side is 3 meters. So if I talk about our displacement, our distance is just 5 meters, right? But our displacement is our change in position. We started here and we ended up at the end of the 3 meter route. So this is our displacement. This is our displacement. Notice that this makes a right angle. So if I wanted to find how far away I was, that would be super easy, right? It's a right triangle. So I could use the idea that the hypotenuse squared equals x squared plus y squared, or the form that we use is, we call this the resultant vector. So we use an r for it. Squared equals the x component squared plus the y direction squared. So what this means is that if you walk 2 meters to the north and 3 meters to the west, you're going to end up here, which is a certain distance in a certain direction from where you started. And we're finding that distance away from where we started. So if I want to find that hypotenuse, it's just going to be equal to negative 3 meters squared plus 2 meters squared. Notice that the negative is going to go away, so that's 9 plus 4, so it's the square root of 13 meters squared. I'm going to put this in my calculator because we don't generally use keep things in radicals in physics. We like decimals. So we're going to take the square root of 13, which is going to be 3.6. 3.6 meters. So we ended up 3.6 meters from where we started, but now we need to describe where we are. Well, let's put this kind of on a mat, on a axis. So I'm just going to draw in the XY axis here right at where I started from as the origin. So I started here and I ended up over here, 3.6 meters. So how could I describe this? Well, I could find this angle here if I wanted to. And if I did that, then I would have to use one of my trig functions to find it. But I couldn't just say that I was 30 degrees away from where I started. I would need to be more specific. How would I describe this angle? Well, if you look at my resultant vector, my displacement vector, that vector is the west of the north axis. So remember, this is north, this is west, this is east, and this is south. So if I find this angle, I want to give it kind of a direction, something to describe. And I don't want to say northwest, because northwest means it's directly in between at 45 degrees. It is not. So I'm going to find this angle using trig, but I'm going to describe it west of north. If I had found the other angle, that angle would be north of west. That's one way to describe the direction. Let's find that angle. All right. So that angle is across from the 3 meters, and it is touching the 2 meters. So 2 meters is adjacent to it, and 3 meters is opposite it. So let's remember our functions. SOHCAHTOA. Sine of the angle is the opposite side over the hypotenuse. Cosine of the angle is the ratio of the adjacent side to the hypotenuse. And tan of that angle is the ratio of opposite to adjacent. So which one of these would be best? Well, I have the adjacent and the opposite side. So I'm going to want to use tan, right? So tan theta of the opposite side, 3 meters, to 2 meters, the adjacent side, is going to give me a decimal. And once I find that decimal, then I'm going to take the inverse tan on my calculator. I'm going to make sure that I'm in degree mode. So if I take the inverse tan of 3 over 2, and make sure you're in degrees and not radians. So inverse tan of 3 over 2 is 56 degrees, 56.3 degrees. So if I'm going to describe this displacement, my displacement vector is, the magnitude is 3.6 meters, and the direction is 56.3 degrees west of north. Okay, so that tells me exactly where I ended up, west of north. Now that's one way to determine that. Okay, another way to determine the direction is to give a polar heading, and we'll talk about that in a little bit. But you notice that it was a little more complicated than just adding 3 meters and 2 meters and assigning a positive and negative direction. Couldn't do that. I had to use trig, and I had to use Pythagorean theorem to add these vectors. So let's talk about vectors in a little more detail. So every vector has a magnitude and a direction. And the way we're going to model this is we're going to assume that when we look at the vector, it's made up of 2 vectors, an x vector and a y vector, or an x side and a y side. It has a hypotenuse, which we're going to call the resultant. It has an x and a y. So just imagine that this is on a xy axis, like that. And we're going to have an angle. And the angle we find in this formula is always across from the y. Okay, it's always across from the y. Now, the last example was a little different, right? It wasn't. It was across from really the x vector, the horizontal part, the horizontal of that triangle. But this is the rule of thumb that we're going to use. So, anytime we want to find the magnitude of a vector, we need to use Pythagorean theorem. And anytime we want to find that angle, we need to use tan theta, where tan, as long as theta is across from y, is equal to y over x. But there may be some situations like the previous one where you have to think about it a little. So let's talk a little more about those directions. So let's say that we have a vector that maybe somebody walked 10 miles to the east and then walked 20 miles to the south. So that resultant would start where he starts and be pointing at where he ends up. So we want to find this length, and the angle that we're going to choose is the one across from the y. So y is always a horizontal. So this is the angle that we want right here. Okay. So if we find r is going to be equal to the square root of 10 squared plus 20 squared, which is 100 plus 400, or square root of 500. And that's going to be 22.4 miles. And tan theta is going to be equal to 20 miles all over 10 miles. And if I take the inverse tan of that, inverse tan, 20 divided by 10, I get 63.4 degrees. Now, how would I describe that? Well, do you see that that angle is below the east axis? So that means that it is south of east. Let's look at some other examples of how different angles. So let's say that I had a vector that was up here, and I saw that its x was in this direction and its y was in this direction, and I picked this angle right here. Well, this angle is touching the west axis, and this angle, whatever it is, would be north of west. How about this one? How about this angle? It would be north of east. How about this one? Well, it's east of the north axis. So I could describe either one of those if I want to. The same heading, right? The same heading. Now, I like to use a more compass-related directions, something that you're used to in math, and that's a polar angle. And the polar angle, by definition, sets the east axis as 0 degrees, and north is 90 degrees, west is 180 degrees, and south is 270 degrees. And what we do is we measure the angle from the east axis between the east axis and that vector. So let's do an example. Let's say that we are traveling. I'm just going to make some let's say this is 20 meters and this is 20 meters. Okay. And let's say that I find this angle here, okay? If I do want to find that angle, I'm just going to take tan to the -1 of y all over x, and the y variable is 20 meters, and the x variable is 20 meters. And if I take tan -1 of that, I should get 45 degrees. Now, if I said the heading was 45 degrees in polar language, in polar language, then what would happen would be measured from 0, 45 degrees would be in this direction. And that is not the direction that that is traveling in, right? It's not to the northeast. It's actually to the southwest. So how do I correct for it? If I'm finding an angle in the third quadrant, I'm going to try to find the angle all the way over here. So if I found that 45 degrees, I just need to add 180 to both sides. So that would be 215. If I find an angle and it's in the second quadrant, then it would be from the east axis, it would be just 180 minus whatever that angle is. If I'm in the first quadrant, it's just whatever that angle is. And if I'm in the third quadrant, it's 360 minus that angle. So, for example, if I have a heading of 150 degrees, right? I would start here, I would go to 90 degrees, and to, well, if this is 90 degrees, then if I go 60 more degrees, this is a heading of 150, and that is 30 degrees from 180, right? I would have used tan theta, I would have found 30 degrees, and I would have subtracted it off of 180 to get 150. All right, so we know how to find the vector direction and the vector magnitude using tan theta and Pythagorean theorem. But what if I just give you a vector and I say a plane is heading, actually let me erase that. My pen died, so I'm going to have to use my finger, and I apologize for that. So let's say I have a force of 200 newtons and it's directed at angle 230 degrees. So 230 would be all the way 180 plus 50 more degrees. So that's my vector. So if I want to resolve this into its x and y components, well, it is kind of like describing a point, right? It has an x component that's about right here. So it has an x component that's right here. And it has a y component that hits the axis down on the south. So it's got this component, that's the y component. This is my x, this is my y, and this is my magnitude. So if I want to find x, how would I do that? I have 200 and I have 230 degrees, or I could use the complement of that, right? I could take 180 off of that, and that would be 50 degrees. I'm going to use the 230 because it turns out that when you take cosine and sine of 230 and its complement, then and its reference angle, then you get the same values, number values, but it points in the right direction. So we're just going to keep it at 230. So if I wanted to find that x is the adjacent side, and the function that has adjacent and hypotenuse in it is cosine theta equals adjacent over hypotenuse. So the adjacent side is equal to the hypotenuse times cosine of theta, or in our values, in our symbols, it's r cosine theta, as long as we're dealing with a polar heading or an angle that is touching that x. So if I want to find that, it's just going to be 200 newtons times the cosine of 230 degrees. Notice that it's pointing to the west, so it should come out to be a negative number. Let's see if it does. 200 cosine of 230. Yep, it is negative 129 newtons. All right. If I want to find the y side, and I know the hypotenuse and the angle, then I'm going to use sine theta equals opposite over hypotenuse, or opposite side equals sine, h times sine of theta, or our y value is equal to r sine of the angle. And r is 200 newtons times the sine of 230. And so that equals 200 sine of 230, should also be a negative number because it's pointing down to the south. That equals negative 153 newtons. So what this tells me is that the vector 200 newtons with a direction of 230 degrees is also the vector negative 129 newtons, comma, negative 153 newtons, like a point in space, like a Cartesian point, and x, and y. Notice that this is in the third quadrant, right? So if I wanted to find my magnitude, I would just take 129 squared plus 153 squared, take the square root, I would get 200. And I would take negative 153 divided by negative 129 and take inverse tan, and I would get this. This would end up being 50 degrees. And then I would have to add it to 180 to get 230 degrees. Or I could just call it 50 degrees south of west. Same vectors. So every vector has an x and a y component. So one thing that you need to be able to do is, if I give you the magnitude and the direction of a vector, you should be able to find its x and y. So remember that x equals r cosine theta and y equals r sine theta. So if I make a chart here of x's and y's, and I have 60 newtons at 120 degrees, I'm just going to take 60 times 1 cosine of 120, and that's going to be negative 30 newtons, and 60 times sine of 120 is going to be 52.0 newtons, and it's positive. Now, does that make sense? It's 120 degrees. Well, 90 degrees is here, so 120 would be somewhere like that. So it's in the second quadrant, right? So if I were to find that angle, the reference angle, I would take 52 divided by negative 130 and take the inverse tan of that. And because it's in second quadrant, I would have to subtract it off of 180 to find the polar heading of 120. So the next one is 100 meters at 90 degrees. Well, that's pretty simple because you don't even have to do math for this, right? If I do that, it's pointing straight north. So how do you describe a point on the y-axis? It has no x. It has no x component, and its value is the y component. So the y component is 100 meters. And then last one will be 200 meters per second at 210. I get negative 173 meters per second for x, and I get negative 100 meters per second for y. also need to go backwards. If I give you the x and the y, you should be able to find the magnitude r and the direction. So let's do just a couple of these to see if we understand what's going on. So the first one I'm going to do has an x of positive 20 and a y of positive 60. So x, y, and this is my r. So r is going to be the square root of 20 newtons squared plus 60 newtons squared, which is 400 plus 3600, which is the square root of 4000, which is 63.2. So R is 63.2 newtons. Notice that I'm not dropping my units when I do these problems. Next thing I'm going to do is I'm going to find its direction. The first thing I'm going to do is I'm going to find the reference angle, and then I'm going to adjust for what quadrant I'm in. The good news is that these are both positive, so I'm in the first quadrant, so whatever my angle is, that's what my angle is going to be. So tan to the -1 of 60 newtons divided by 20 newtons. So inverse tan of 60 divided by 20 is 71.6 degrees. So this is 63.2 newtons, comma, 71.6 degrees. Let's do the third one, 10 and 20. Okay, so for 10 and 20, it's -10 and -20. So -10 and -20. 10 and 20. So my hand is so big I can't even write in the units right now, but we'll do that when we do the math. So I'm just going to find R, which is just a square root of -10 newtons squared plus -20 newtons squared. I'm going to square root all that. I should get the square root of 500, which is 22.4 newtons. So I'm not dropping my units on the answer. And now I'm finding this little angle here. That's in the third quadrant. So I'm going to have to add it to 180 to find the polar direction. But first I got to find that reference angle. It's going to be equal to the inverse tan of y, which is -20 all over -10 newtons and newtons. And if I do that, the inverse tan of 2 is 63.4 degrees, but it's in the third quad. So I'm just going to take that and add it to 180. And when I do that, I get 243 degrees. So this one is 63.4 newtons at an angle of 243 degrees. If I'm in the third quadrant, I'm going to subtract it off of 360. Of the second quadrant, I'm going to subtract it off of 180. Those are my rules. So in your first homework, you are asked to give all your directions as polar coordinates. So you want to use tan theta and then adjust for what